Hi everyone. Imagine a small, grey vessel, built for a purpose that sounds almost unreal, to survive underwater nuclear explosions. Not a submarine. Not a warship. Just an ordinary-looking working barge. Its real name is BUMS Y1689. And it's the only vessel in the world that deliberately placed itself into underwater atomic shockwaves, just to test the nerves of submarines. So how did it survive all of that? Officially, it's known as Bundes-Unterwasser-Mess-Schute, Class 740. Since 1960, this ship has remained one of the most unusual, and most secretive, test platforms of the German Navy. This is where the Bundeswehr pushed the limits of naval engineering. Powerful underwater charges are detonated close to the hull. Shock waves ripple through the structure. Sensors record every vibration, every strain, every structural response. The goal? To find out whether submarine systems, and entire vessels, could survive a real underwater blast. Because underwater explosions don't behave like those in the air. They are faster, more violent, and far more destructive to anything submerged. And right at the center of these brutal tests stands BUMS Y1689. Today, for the first time, we're going to take a deep and detailed look inside this unique vessel. We'll explore air design plans, break down the engineering that allowed it to survive where others would be torn apart, and uncover the logic behind its almost ironic name. Because in German, BUMS sounds exactly like what it represents. A blast, an impact, a sudden, violent shock. BUMS, the Federal Underwater Measurement Barge. There's hardly a more precise way to describe the function and purpose of this Class 740 vessel. On April 28, 1960, the shipbuilder HDW delivered this highly specialized platform for naval research. At just 26 meters in length, with a maximum beam of 6.42 meters and a displacement of around 200 tons, BUMS is a compact vessel, but one with an extremely focused mission. Its steel hull features a shallow draft of only 2.21 meters. And is deliberately designed to be unusually wide. This shape isn't accidental, it's critical for stability. To further enhance that stability, the vessel uses a double hull construction combined with ballast tanks. The entire structure is built to be exceptionally strong and reliable. After all, this ship operates in immediate proximity to explosive detonation zones. The frames are closely spaced. The outer hull is reinforced. The shallow draft and solid geometry all contribute to structural resilience. And every piece of technical equipment on board is mounted with shock-absorbing elements, designed to survive violent underwater impacts. BUMS is powered by a diesel-electric system. Inside the engine room operates a compact inline six-cylinder engine, the MWMD-226, connected to a generator. Interestingly, the diesel fuel tanks are positioned high on B deck, just behind the steering console, and intentionally placed far away from what the crew calls the boom zones. Most of the generated electrical power is used for propulsion. At the stern, the vessel is equipped with an active rudder system, combining propeller and rudder into a single unit. This configuration provides superior maneuverability at low speeds, while also reducing the overall rudder surface area. And that's critical, because during shock trials, the vessel must maintain a precise position within the blast zone. That requires maximum control, even at minimal speeds. However, with only 90 horsepower, BUMS is not built for speed or comfortable cruising. During the design phase, a conventional propeller system was also considered. But it was ultimately rejected, deemed too dangerous for operations involving explosive testing. Interestingly, original plans still show this alternative configuration. At the stern, a loading crane was installed, intended for handling measurement equipment. With the exception of the hook block, the crane is still operated entirely manually, raising and lowering the boom, rotating it left or right. All of it is done by hand. Today, measurement devices are often no larger than a laptop, easily carried under one arm. But the crane remains fully functional. It can still lift equipment through a traditional cargo hatch, covered with wooden beams and tarpaulin, directly into one of two measurement compartments below deck. Inside these compartments, sensors are connected to the test setup via cables. Data is collected here, and from this very space, the detonation itself is initiated. Thanks to a powerful compressed air system, based on a Junkers piston compressor, BUMS can precisely lower and raise what are known as shock modules. These include specialized submarine sections, and even entire submarines, fitted with sensors and explosive charges. When a test object needs to return to the surface, compressed air is used to force water out of its compartments. Quite literally, it is blown clear. Even the anchor winch at the bow is powered by compressed air. At the time, this was a true innovation. Because the original documentation was still available on board BUMS, it became possible to create a model with an extraordinary level of detail. A well-known naval architect, F.W. Besch, meticulously recreated the vessel down to the finest elements, across 5 large format drawing sheets. In addition, numerous photographs taken on board during the construction phase played a crucial role in the design process. To achieve this exceptional level of accuracy, a scale of 1 to 20 was chosen. At this scale, the model measures 130 centimeters in length, 32 centimeters in width, and has a draft of 11 centimeters. The result? A model weighing approximately 25 kilograms, solid, stable, and remarkably steady on the water, barely reacting even to small waves. Its displacement is sufficient not only for stability, but also to support a wide range of functional features, while still delivering realistic handling characteristics. And that brings us to one of its most fascinating aspects, the propulsion system. For a technically skilled model builder, recreating the original active rudder system is entirely achievable. With the widespread availability of brushless motors, the required performance can be easily delivered within the compact propulsion gondola. The relatively small propeller is perfectly suited for high RPM operation, making it an ideal match for modern brushless drives. However, for those who prefer a mechanically simpler solution, there is an alternative. The original design once considered a conventional propulsion system, and the plans still allow for its implementation in the model. The hull itself is straightforward to assemble. It features a hard chine construction, with no major structural complications. True to its real-world purpose, the hull is reinforced with closely spaced frames. All of them are shown in the drawings, but in the model, only every second frame needs to be installed. But the real challenge lies in the details. Take the rivets, for example. The plans show every single one of them. And when it comes to detailing, the possibilities are almost limitless. The BUMS model impresses with an incredible number of intricate features. From the anchor winch on the foredeck, to the superstructure with its mast and antennas, to the large ventilation units, and finally, the striking crane at the stern, every section reveals something new. And if desired, parts of the interior within the superstructure can also be fitted out. With the doors open, the compressed air system becomes visible, complete with pipes and fittings, faithfully reproduced. And the included illustrations help bring the entire structure to life, making the design easier to understand and even more rewarding to build. It's a model that truly stands apart from conventional builds. BUMS, from its name to every line of its hull, from the keel to the very top of its mast, is something entirely unique. Thanks for watching.